to Euler equation of mixed and radial flow machines. Now we have talked about, in the previous slides, we have talked about general Euler equation of a rotor, for a turbomachinery rotor, and then we have talked about Euler equation of axial flow machine. And right now I would like to talk about Euler equation of mixed and radial flow machines. Now with radial flow machines, what do I mean? Let's start with radial. Radial flow machines, you have, we're talking general here, we are not talking about pumps or turbines, we're talking very general. So in radial flow machine, you have the fluid entering the rotor radially and leaving radially, okay? And here in this case you have the fluid entered at a mixed, not really axial, not radial, but a mixed scenario, and leaving at a mixed scenario, okay? So that's the meaning, that's the main difference between radial and mixed flow machine. It's classified into radial and mixed based on the direction of the flow, either because this is the axis of rotation, okay? So either you have a meridional component of the flow velocity. There's meridional mean not axial, not radial, in kind of between. So that's the meaning of meridional component. So you have a mixed between the radial and axial, and here you have a purely radial. Now the area of the flow at the leading edge, if you are talking about radial flow machine, is this guy, 2 pi r1 b1, and the area at the trailing edge is this guy. But if you are talking about mixed flow machine, then the area of the flow at this mixed position, it can be represented as this guy. So the area of the flow at the leading edge at this point can be calculated with this formula, and this is the area of the flow at the trailing edge, okay? So just be aware of this when we talk about mixed and radial flow machines. Now this is the basically the velocity triangle for either radial or mixed flow machine when you talk about pump, fan, or compressor. And if you are talking about turbine, this is the typical velocity diagram for the inlet and outlet sections of the flow. Now this is the present. If you are having a swirl free at the inlet, then again there will be no tangential component of the absolute flow velocity, and that's why we are having no trace for the tangential component of the absolute flow velocity here. But in contrast, if you are talking about the of course the trailing edge, then of course you have swirl flow at the outlet, or otherwise this will not be called a power consuming machine, because you want to maximize the tangential. This is because, remember, the maximum energy transfer can occur if you have swirl free at the inlet. In this case we have C, if you remember, Cw equal to 0, okay, and Cw1 since we are at the leading. But of course you do want to have Cw2 at the outlet equal to 0. This is not right. If this happens, then there will be no energy transfer, because if you remember, the energy equation for a pump is just equal to what? C omega 2 times U2. So there is no way. This is for a pump, fan, or compressor, and the opposite is true for a turbine. So for a turbine, you need to have maximum swirl at the inlet. So C omega 1 needs to be at its highest value times U1, okay, the rotor speed. So just be aware of these. And then the unlike axial flow machine, the fluid, the blade angle is making a degree with respect to the relative flow velocity. I mean, it's making an angle between the rotor speed and the relative flow velocity. It is different from from axial flow machine. You need to check and go back and see what are the differences for the velocity triangles between axial and radial and mixed flow machines. Okay, so let's take an example for right now. Let's take an example pertaining to radial flow impeller. So we have a radial flow impeller. Okay, this is the axis of rotation. Now we have the inlet to the rotor. We have the flow entering the rotor at a radial distance of 3 inch. And we have the flow leaving the rotor at a radial distance of 9 inch. And it's telling you that the speed, the revolution per minute for this rotor is 800, and it is pumping water at this much gallon per minute. It's asking you to determine the radial flow velocity. And now this is a radial flow machine. So remember, the blade angle, we have swirl free at the inlet. We can assume swirl free at the inlet in order to get the maximum energy transfer between the rotor and the fluid. So, but first we will proceed typically by calculating omega in pi over 30, which is around 84 radian per second. Now, next we'll calculate the rotor speed, the linear rotor speed, which is omega times R1. R1 here is in inch, 3 inch. So when you do that, you need to convert it to feet in order to get the unit as feet per second. Okay, and similarly you calculate U2 as what? As U2 times R2. So R2 here is 9 inch. U2 is different. Remember, it's not an axial flow machine. If it's a radial flow machine, then the rotor speed at the leading and trailing edges will be different. So the radial flow velocity is always equal to the flow rate. Radial flow velocity meaning this is the axis of rotation, and we have the radial flow velocity this way. Okay, now V, remember in the beginning I have told you that in some cases you'll find me representing the absolute flow velocity as C. Here in this example I'm representing the absolute flow velocity as V. So just be careful of the notation difference. Okay, so with that let us move to the next example. So next example also talk about it's also actually related to the previous example in some sense, but the thing you hear is that the inlet flow is swirl free and the rate of flow direction decreases by 10 degree. So the relative flow direction decreases by 10 degree, meaning that the flow angle at the outlet of the rotor is just less than the flow angle at the inlet by how much? By 10 degree. That's the meaning of decreases by 10 degree with respect to the tangential direction from the inlet to outlet. So it's asking you to determine all flow velocity at the inlet and outlet, and plot also the velocity diagrams. Now this is a radial flow machine, and since it's a radial flow machine, we have the flow angle making a degree of this much with the relative flow velocity at the outlet. So the angle between the rotor speed at the trailing edge and the relative flow velocity at the trailing edge is this much, beta sub f2. Now this guy, okay, so this guy, this is the whole thing is U2, and then of course the other thing you have to draw, because the head of the rotor speed should be the tail of the relative flow velocity, and then you close the triangle with the absolute flow velocity. Now the direction normal to the u, because u is the circumference in the tangential direction. Now the direction normal to this will give you the radial flow velocity component at the trailing edge. So you do all of that. This is the velocity triangle of this bump, and this is the inlet velocity diagram while assuming there is no square at the inlet. Okay, with that being said, we can calculate this guy by saying tan beta sub f1 is just equal to v1 over u1. Okay, and or another scenario, we can also calculate tan beta sub f2 as vr2 over the tangential component of the relative flow velocity, which is w sub u2. You do that and you do all the calculation, and you can calculate the tangential component of the absolute flow velocity at the trailing edge as around 43.4 feet per second, and you can calculate the relative flow velocity, and you can see that the tangential component of the absolute flow velocity is much higher than the relative flow velocity, which is making sense. So this is the responsible for the energy transfer from the rotor to the fluid, and this guy gives you the absolute. So you see here the absolute is very close to the tangential, meaning that most of the kinetic energy has converted into a tangential velocity, which is good, which is actually will result in producing higher angular momentum on the fluid. This is another example, but this example actually talks about turbine. It's not talking about pump. So in this example, we are talking about turbine, and it's the direction of flow is reversed. You see here the fluid is entering radially and leaving the turbine in the mixed direction. So that's why here now the velocity triangle is different. Now if we assume square free at the outlet, we assume square free at the outlet so that we can get benefit or we can get maximum energy transfer utilizing the absolute flow velocity at the inlet. So it's asking you to determine the ideal output shaft power. Now we all know that, well, the ideal output shaft power of this turbine, B sub T for example, is just equal to what? The mass of the fluid transferred through the rotor times the rate of energy transfer between the rotor and the fluid, which is represented here as delta E sub T. Now delta E sub T is the Euler equation. Delta E sub T, as you can see here, is the rotor speed at the leading edge times the tangential component of the flow velocity at the inlet. So you calculate, of course, the flow rate. Now why we have V sub M2? This is meridional component. Meridional component because we have mixed flow at the inlet, mixed direction, not radial, not axial. Okay, this is the axial and this is the radial. So this guy is leaving like this. So you need to be careful about that. And once you assume square free at the outlet, then you can safely say that the flow angle at the inlet is equal to the plate angle at the inlet, and similarly for the outlet. Okay, so here we have another example talking about Francis type hydraulic turbine. So the flow is entering radially with respect to the axis of rotation and leaving actually in the mixed direction, and it's asking about the ideal output shaft power. Again, the ideal output shaft power is this. Now you need to calculate the energy transfer and then multiply it by the mass. So but in order to get VU1, you need to do some calculations, some steps ahead. The main point, VU1 is just U1 minus minus the tangential component of the relative flow velocity, which is this guy. So this is basically, okay, this is basically this distance. So this represent what? This represent the okay, now we have here for example we have V U1, but here we have W U1. Think about that. And then we have radial flow velocity at this guy. So from this relationship you can find out, you can actually derive, or you can actually reach into this expression. Okay, so W1 is just VR1 tan beta fluid, or in other words, tan beta fluid is just the مقابل على المجاور. Now this مقابل is VR1, مجاور is W1, the tangential component of relative flow velocity. You do all the calculations and you get the shaft power of this turbine around 6.5 kilowatt. Now let's talk about the component of energy transfer in turbo machines. So right now we have known about the typical Euler equation for a rotor of a turbo machine. We have then talked about the Euler equation of axial flow machine, and then we talked about the Euler equation of mixed and radial flow machines. Right now I'd like to talk about the components of energy transfer. So remember this guy, this is the velocity triangle at the trailing edge, and this is the velocity triangle at the leading edge. It's a typical diagram representing the velocity vector of the flow at the inlet of the plate and the outlet of the plate. So here in this case we have always the radial component. See here represent the absolute flow velocity. In the examples of this lesson, the absolute flow velocity was denoted as V, but in the theory of this lesson, the absolute flow velocity was denoted as C. Just be aware of that, and I have written it explicitly on the example. I have stated that I am using the letter V as the absolute flow velocity, but here we have the absolute flow velocity as C, and we have always the radial component normal to the axis of rotation. This is the axis of rotation, right? Or if you will, this is the axis of rotation, and then we have the radial component C sub R1. So this is C sub R1, radial component of the absolute flow velocity, and this is also C sub R2. Now C, from this relationship we can state that the radial component of the flow velocity squared is equal to the absolute flow velocity squared minus the tangential component. So basically you can say that this is the summation of C1, or if you were to look here, C1, C2 term squared minus this guy. This will give you C sub R2. Okay, C sub R2, explain, make it clear for yourself. This guy represents C sub R2, and similarly this guy represents here C sub R1. Okay, see, from this relationship we can write this one, and we can also write another expression for the radial components of the flow velocity utilizing this area. I'll make it in another color so you can see. So this is basically, this is one area, another area is in the red region. Okay, so from here you can get an expression for CR2, which is this one, and from this one you can also get an expression for SR2. Make them equal. When you make them equal and rearrange some of the terms, you will get the Euler equation for a turbine, for a pump, compressor or fan as this. So you will get it as this. Frame it. So this is basically when you make this guy equal to this guy, you will get this guy. So okay, when you get this guy, we want to make some arrangements to get an expression for that. Okay, so it's basically the half of c2 square plus u2 square minus v2 square, and just substitute the c square, u square, and v square in the Euler equation for a bump, and you will get this. And for you do it the same for turbine, you'll get this guy. Now this is very important because these are different components, though they are all representing the energy transfer, but they are different component, and everyone has its own meaning. For example, this guy represents absolute kinetic energy change from the inlet to the outlet of the fluid, and this represents the internal diffusion. So basically you have an external effect and you have an internal effect, so it is different. When you so when you divide these two terms by the whole three, we get what is we call degree of reaction. I'll talk about it in a second, but just know for now the half c2 square minus c1 square, or in other words, if you are talking about turbine, c1 square minus c2 square by 2, they are representing the energy transfer due to change in absolute kinetic energy of the flowing fluid during its passage, of course, from the inlet to outlet section. Now we can safely say that in a pump or compressor, discharged kinetic energy, the discharged kinetic energy from the rotor, so the rotor is giving me a kinetic energy that is equal to half c2 squares, and that's what is happening. The pump is adding a kinetic energy to the flow. In turbine, on the other hand, the kinetic energy that is being added by the fluid is half. It is just half c1 square. Okay, so it is half c1 square if you are talking about turbine. Okay, now again we call either this term or that term, we call it external diffusion because it's happening it is happening before the rotor and after the rotor, whereas we call this term the internal diffusion. This is what is happening across the rotor itself. Okay, but this is the centrifugal effect. So basically the impeller is rotating. There is a rotation speed at the leading edge, and there is another rotation speed at the leading edge, at the trailing edge, sorry, and the difference between them creates the centrifugal forces. The last term, half v square minus v square, represent the energy transfer due to the change of the relative kinetic energy. Okay, and of course if v2 greater than v1, then we have a passage that is like a nozzle. But if we have an absolute flow, a relative flow velocity that is actually greater